Building things on your own is not always easy, especially when your lathe isn't that precise as I want it to be. You saw that in the last video when I wanted to build the crankshaft. I will make another video where I try to solve the accuracy problem. But for now, my colleague milled the crankshaft for me the way I wanted. In retrospect, it occurred to me that I could have a stroker crank, but for now it is what it is. I was also smart enough not to oil the crankshaft right away when I got it. That's why there's some rust on it now. I also have special crank couplers with two woodruff keys so that the second cylinder is rotated exactly 240 degrees further than the first. And the third one is twisted 120 degrees further than the first. Now I just press the two crank halves together so I can calculate the balancing factor. Then I build a device for balancing. The most important thing is that the rails on which the crankshaft lies are exactly horizontal. What is also important to mention is that depending on the engine, the oscillating mass of the crankshaft, which means the piston and the part of the connection rod which goes up and down, is only balanced out by about half. This is because if the oscillating mass were 100% balanced, the motor would vibrate very strongly in the horizontal direction. If the balancing factor is too low, the motor would vibrate in the vertical direction. If it were an engine with horizontal cylinders, the whole thing would be reversed. Now I add as much weight until the crankshaft stops on the rails in any position. Now I have determined that it takes exactly 42.55 grams for the crankshaft to be 100% balanced. Now I need to wait for the upper half of the connection rod. And the last thing I need to weight is the piston ring, the upper needle bearing, the piston clips and the piston pin. We take the 32 grams of the oscillating portion of the connection rod and add the 42.55 grams of the crankshaft balance weight, and then we get the effective mass in equilibrium, which is 79.55 grams. Now I calculate the oscillating mass. We take the 37 grams of oscillating portion of the connection rod and add 159 grams of piston bearings and clips. Then we get 137.59 grams of oscillating mass. We take the effective mass in equilibrium, divide it through the oscillating mass, multiply it by 100, and then we get the balancing factor, which is 57%. I'm pretty happy with the 57% of the balancing factor, so I just leave it like that. Since it's supposed to be a 3-cylinder engine, I also have to make sure that the connection rods and piston are all the same weight to avoid vibrations. Now I milled the groove for the key where the bevel gear sits, and then I can assemble the crankshaft. I use parallel plates to ensure that I press the connection pin straight and not crooked. If necessary, I can knock it straight using a copper hammer. There must be a clearance of about 0.5 mm between the crank halves and the connection rod. In order to guarantee a perfect concentricity, the two halves must be aligned with each other. I turn the crankshaft on my test stand until the dial indicators show the maximum height. Then I use a screwdriver to bend this side and balance it out. You can also use a copper hammer. You do this until the dial indicator only shows a few hundredths. About a hundredth difference between left and right. That's completely fine. Because I use a racing ignition from a Kawasaki H2 750, I have an additional cone on the crankshaft that has dowel pins in it. I need this because the inside diameter of the magnet wheel is larger than the diameter of the crankshaft rod. That's all I've got for now. Thanks for watching and see you next time.